which is kind of the subtitle of the presentation, which I usually call how to find every single rabbit hole and jump straight in at first, because there was a lot of that going on during this project. So, who am I? General computer and electronics nerd, have been for pretty much my entire life. I'm entirely self-taught. I think the last official certification I have is implementing and supporting Windows 95. And I have 9 years of basic school, and that's it. I've never even finished the gymnasium, so yeah. Been working in enterprise IT since 1998, pretty much. Most of it as a network engineer. But I've been a software developer, database admin, system admin, you name it, I've probably done it. A bit of a polyglot in IT in that way. That's the links to my project webpage and to my code repositories. Most of the things I do tend to be open source or open hardware, because that's kind of the goal for me, it's preservation. So the background of this project is, that is my first home computer. I got it on my 10th birthday in 1985. I still have this computer. It's been in a moving box as I've been moving through all of these years. And in 2019, I was going through a couple of the boxes. I saw it sitting there in a I think it was a banana box, the usual one. So I decided to just pick it up, plug it in, and just have a bit of fun for good old times. Of course, it was broken. The typical Commodore 8-bit, just a black screen when you turn it on. Sync signal, but nothing else. So I decided, well, I know basic electronics, I can fix it. And at this point, I really didn't have much experience with electronics. I knew half-decent soldering. I could build some basic things using standard digital logic, how to put a reset switch on a C64, you know, the basics of electronics. So the repair got a bit snowballed and gone weird all over the place. So at this point, I was already aware of what Chucky was doing with the Amiga project. I've also been involved and talked a bit with Rob Taylor, who makes the 60 clone and the Amiga 500++ and a few other of these replicas. So as I was repairing my Commodore 128, I realized that the PCB of it was corroded. So moisture had gotten in through the solder mask on the board and actually started corroding away the copper underneath. Poor quality solder mask. It's a Commodore PCB after all. They were cheap. So I realized if I have that problem, other people will have the same problem. So if I can make the same type of replica that they have done, and I know for a fact Rob Taylor, when he started doing his replicas, he did not understand much of electronics, but he understood enough to actually start making replicas of the PCB. So I figured, if they can do it, so can I. Word of notion, if you decide to get involved in electronics, making a replica of this PCB is probably not the best first project. So, one of the things I try to do in most things that I do is, when I come up with a project, I always try to define a mission statement for that project, just to keep myself on track. I got ADHD, I have a very easy time of just sidetracking myself and going off on tangents and never coming back. So I try to always define what do I want to achieve before I start doing things. And in the case of this 128, I wanted to make a direct one-to-one replica of the PCB. I wanted to integrate a few of the factory fixes that they were making at the factory floor at Commodore. So there were a couple of traces they had to cut. There were some components soldered on after work. They never upgraded the PCB, they just did it on the factory floor of the assembly line. And I also wanted to do some small quality of life improvements. What I did not want to do was big changes, like changing the type of RAM chips that were used and adding an extra SID and these type of things, because I knew that if I start doing that type of stuff, I will never stop. So I decided to just keep it at a platform preservation. That also meant that I wanted it to be ultimately open source and open hardware. Because for me, there's no point in me doing a replica unless it will be available even if I get run over by a bus. Then I haven't really achieved anything except maybe a couple of people having a nice PCB, and that's it. So now it's all preserved on Git. Anybody can download it, they can make new copies, they can modify it, they can do whatever they want with it. So as part of that, I selected to use KiCad, because if I'm making an open source project, for me personally, I then want the software used for the project to be open source as well. So that for me is, if I have all of the design files, but I can't access the software used to edit the design files, is it really open source? It's a philosophical thing, and people will have different opinions, but that's my opinion. Rob Taylor and Chucky have used Sprint Layout, which is a small German program that's used specifically for doing PCB only. It doesn't do schematics, it only does PCB work. But it did have the then fairly unique feature of being able to import a scanned image as the background. So to replicate the PCB, you could just import the background image and then click out the traces, just following the line basically, and you'd have a replica. I wanted to make sure that I also had a full schematic capture and everything else to just make it easier to follow along and then later on make modifications, etc. If you don't have the schematic, it's hard to make modifications and make sure you didn't break anything as you were doing, of course. So, another nice thing is Commodore back then used to always publish their schematics. For the Commodore 128, they are incredibly accurate. I only know of 2 mistakes on the schematic in total, which for Commodore is pretty astonishing, especially seeing the quality of the C64 printed schematics, which are so wrong, it's not even funny. I did not attempt to just do a one-to-one replica of the schematic, because that would mean 4 pages in a gargantuan format with lines flying everywhere. And our design software and how we represent electronics have improved significantly since then. KiCad in specific has something they call hierarchical schematics. So, which allows you to use separate pages and then draw links between the pages on a top page, for example. So I decided to try and use that to represent the block diagram of the system. So just have big blocks representing the various components, and then show the interconnects. Of course, at this point, I'm still learning KiCad. So my first attempt was functional, but not very useful, shall we say. So that's the VIC chip, and every single signal going to and from the VIC chip was exported to the global sheet, and then traces flying everywhere, and this is just completely unreadable, of course. So I very quickly moved on, and the schematic today on the main page looks like this. So I moved the individual control signals to use global signals, so they're not represented on the global sheet. And here you can really see the individual data buses and address buses that make up the system and how they're connected and to which components they're connected. So it works really well as a block diagram of the 128 system, which is fairly complicated. It has 3 address buses and a data bus that flies everywhere, but technically 4 address buses if I include the max DRAM. Okay. There you go. So this is vastly better, of course. For the PCB side, it's fairly straightforward. You put your PCB in a flatbed scanner. By the way, rabbit hole, I had to find a large enough flatbed scanner to fit the PCB. Fortunately, work had some nice Konica Minoltas with an A3 scanner, which worked. You import the background as images. You place down the components as required to match from the schematic. And then you just draw out the traces like the red ones here, for example. What you do need to bring yourself is patience. lots of pins. Every single bend on these traces have been hand drawn out, pretty much. This is maybe a tenth of the entire PCB. It's equally densely packed pretty much across the entire board. The 128 is 16 by 10 inches in size, and pretty much the entire PCB is packed like this. It's insane how much stuff there is on there. That took me on and off about 3 months, working a bit on weekends, and after work you can't sit there for a whole day because you would burn out. Put some nice music on, do a couple of hours, and then save it and come back tomorrow or whatever. So I said, for me it took 3 months. For the original Commodore engineers who did it, it took 1 week. And they were not copying, they were actually designing it and figuring out where to place the components and do all of the routing. 1 week, 4 guys. These 4 guys. Because when they were finished, they put this comment on the bottom of the board. So Bill Hurd told me that these 3 guys, Fish, Dwyer, and Parr, they are board layout engineers, or were board layout engineers at Commodore. They were inside of a small office room where they had a very high air conditioning, like a server room, to cool the electronics CAD workstation that they had. These 3 guys were working 8-hour shifts, so 24/7 for the whole week. And Bill was around to answer questions, etc. And when he wasn't needed, he would sleep under the table. So they would just kick him, ask something, and he would go, "Oh yeah, that," and then go back to sleep again. So, but by the time they were done, they were completely done. They didn't work the week after, he said. So anyways, that's the first prototype board I got. I ordered the PCBs to be printed. You get 5 of them as the minimum. There were some mistakes made, like the pinout for the AV DIN connector. The component didn't actually fit in the footprint. That was fun. The RF modulator footprint was also not correct, so I actually had to cut off the little grounding pins on the RF modulator to get it on the board in the first place. You need to have it on the board, otherwise there is not going to be any picture even on the AV connector. And a few other minor things like that. However, much to my absolute shock and surprise, it worked on the first try. I powered it on and it gave me this picture instantly. Except it has a bit of a problem with the upper and lowercase character. Well, short story long, there is a little adapter board on the boards like this, on the machines that were made for international markets. The EEPROM chip used by the US ones has a rather unusual pinout. It's a 2364 mask ROM, which doesn't match the normal EEPROM footprints or pinouts that you use. So the international companies made this little interposer board to adapt a normal EEPROM to that socket, which requires this little extra pin for an address line to be soldered on. And on my first prototype, I had forgotten to connect this one. And due to happenstance, this line here is actually what selects between the upper and lower case on the font. So what happened was, since that address line was disconnected, it kind of floated with the address line next to it, and that's why which letters are upper and lower case are consistent across the board. They always look the same. So, but once I figured that out and soldered the pin on, it worked just perfectly fine. So I'm still absolutely shocked and waiting for it to explode because nothing works on first try. So, but yeah, that was the replica part of it. And I said I did integrate some of the factory fixes into it. I will just show one of them, which is R102. So this is, on the factory, they did it like this. There's a trace cut on the top of the board, and there's a resistor soldered in between 2 connections close to that cut trace. This controls the read-write line and splits the read-write line into the 1 megahertz line, and splits it into two halves between the resistor, one half of the board and one half of the board, and the resistor in the middle. The reason for that is to do impedance control. A rudimentary form of impedance control, because back when they did this in 1985, they had never heard of the word impedance and they didn't know what it was. It was kind of not really a thing in board layout at that point. So you would do fixes like this going on. So what I did was I just integrated into the board. I did so with quite a few of the other little small fixes they did on the factory line as well. Because if you buy a new PCB to replace an old one, I don't want to take a knife and cut a trace and install a watch wire on the first thing I do on my new shiny PCB. That's just silly. So that made sense to me and is worked pretty nice. Forgot to change the title on this one. That was revision 1. Since then I've gone through 5 revisions. 6. So the current board is revision 5. I will soon start selling them. So this is a revision 5 board with a few more quality of life fixes on them. You have more pin headers for various expansion boards you want to do. You might want to hook up the signals. I brought them out, so you have the 1 megahertz and other control lines readily available as pin headers, so you don't have to solder into things. Some components have been replaced. So on the normal 128 you have a big long actual catalytic here. Those big ones are getting really hard to find, so I replaced it with a more modern, smaller radial one. Actual radial, yeah. Yeah, there has the factory original one. So I just made a dual footprint where you can select which one you want to use. This one is much easier to get a hold of today. So, and that's been a theme as well. There's quite a few things where components have become harder to find today. So I tried to replace them with easier options today. 2 other things I've done that's fairly large compared to the original board is I built an RF modulator replacement into the board. So you don't have to install the RF modulator because who connects through the antenna connection on a TV today? TVs don't even have antenna connections in general. So it made sense to just put a replacement in there. It's there, you don't have to populate it. You still have the footprint for the RF modulator if you want to use it. I've also replaced the power connector. So the original Commodore 128 has the same square power connector as the Amiga does, the 500 and 600 and 1200. That connector is absolute unobtainium today. You cannot buy one. The last manufacturer of them, when Jens Kernfeldt at Individual Computer ordered his last batch from them, I've been told that their injection mold tooling actually expired during that production run. So they no longer have the injection molding tools to manufacture those connectors. So when he's sold out, they're gone. And that's going to be a problem for Amigas going forwards as well. So if you want to build a replica Amiga, you will not be able to find that power connector. You have to scavenge it from an existing Amiga or come up with some other solution. So what I decided to do on the 128 is fairly straightforward. I replaced it with a round powered in from the Commodore 64 with the same pin out. So now you can use an aftermarket C64 power supply, which you can find almost anywhere, to power your 128 instead. It's not what I would prefer to have done. I would have liked to have those connectors readily available. They are not, so what do? You choose the pragmatic solution. The drawback is if you plug in a standard Commodore 64 death brick into one of these, that death brick will explode because it has a 7805, which are rated at 1.5 amps. This will draw 2 amps out of the box. So that's going to have to be a big warning I will put in the documentation for this machine. You cannot use a standard C64 power brick. It has to be able to do at least 2.5 amps minimum. Another change I did, that was on revision 4, is the Commodore 128 has a lot of jail bars. We all know it. Lots of happy vertical lines at the display. They're really bad on the 128. What I did on the revision 4 is the video output connectors, which are these two pins here on the big chip, are right next to some of the noisiest signals in the entire computer. You have the 1 megahertz clock, you have the RAS for the DRAM, you have the BA and ASC signals from the big chip, which are also high frequency noise on the surrounding pins, and with traces going right over the video signals at all sorts of angles. So I decided, just for fun, at this point, I have learned quite a bit more about electronics. Still not an electronics engineer, I just learn as I do. What I did do was I decided to put guard ground signals around it to basically make mini coax on the PCB to see if I could protect the video signals to avoid the interference from those noisy lines that are sitting next to it. I also made sure that any crossing was absolutely perpendicular once again to minimize any interference going on. Yay. And I got back the revision 4 board, I turned it on, and I was absolutely shocked that there were no jail bars. They're gone. They will show up very faintly if you use an upscaler who tends to be more sensitive. If you use a Commodore CRT, you will not see any jail bars at all. They are gone. So I'm very, very happy with that result. And that's the small kind of quality of life fixes that I tried to do on this board. As I said, you have the DRAM sitting down here, 16 chips. I could perhaps have replaced them with the 4-bit 4464s, but that would mean I would have to relay out that entire section of the board, which is some of the most timing critical parts of the entire PCB. In fact, when they did the original design, they put those DRAM chips in first, made sure they were absolutely happy, and then put the rest of the board around it. Because most 8-bit computers is all about keeping that DRAM happy. There are no wait states, there's no bus arbitration, you have to have a good response from the DRAM straight off as soon as you ask. Yeah. So I didn't want to do big work like that, because then I might just as well redesign a whole new board. There are issues with the 128 design. It doesn't have a ground plane. It doesn't even pretend to have a ground plane. I usually call it the Swiss cheese ground plane, because there are little ground traces here and there and there, and yeah, it's literally absolute Swiss cheese. So signal quality on it is not great, but it's a working machine, so I'm not going to mess with something that works, of course. Of course, I'm an absolute lunatic, so I did it 2 times more. So the 128 and the 128D, the plastic 128D, they have the same PCB. They just populate it slightly differently to make it a 128 or a 128D PCB. There is, however, the 128D CR, which is the metal 128D. That one has a completely different PCB. I'm currently replicating that one. And the one you have on the screen here, which is a Commodore 128, it does not look anything like this board. They are very, very different in board layout, as you can probably see. This is what's called a 128 CR, cost reduced. It was, to the best of our knowledge, designed by one of the Commodore engineers in Braunschweig, trying to make the Commodore 128 cheaper to manufacture. They were never officially released as a product. Some boards were sent out as replacement board for repair, to repair workshops. Some boards were put into Commodore 128 cases, which is funny because this board is actually smaller than a normal 128 board. You can see it down here. Here's the normal screw hole, and there's the one on this one. So you can actually recognize these ones by flipping a 128 side upside down. And if you see heat set inserts, small brass inserts in the bottom of the case, is one of these, because that's what they did. They drilled a hole and put a heat set insert into it. Less than 10,000 of these boards are known to exist, going from serial numbers. We have no idea how many of them actually exist. So I managed to buy one from a bloke in Italy and desoldered everything and made a copy of it. So that's available on Git as a full open source project as well. So I'm also actually working currently on the Commodore 128D, the 1571 drive that's built in, has a separate PCB inside of the case. I'm working on reverse engineering that board. I'm also making a mechanical keyboard. I have a prototype on the desk over there. And all of this stuff is available on Codeberg. I moved off GitHub to Codeberg in Germany. So yeah. Meanwhile, while this was going on and I'm making the new revisions and the other boards, etc., I bought a microscope, which is one of those standard SM40 soldering type microscopes. Just because I started to do more and more electronics on the side, not related, so I wanted to be able to work on surface mount components, and for that you want magnifications. So I found some videos on the internet, on YouTube, about people taking ICs apart and taking pictures of them, so I figured, hey, I have a microscope, I can do that. And then you quickly learn that in order to get the black epoxy casing away from an IC, you need to use some pretty nasty chemicals. In fact, what you'd use industrially to do so is you're spraying the package with red fuming nitric acid at 60 degrees centigrade. Not something I want to do at home, even if I could even buy that acid, thank you EU. It's not very nice, and there's not many other ways of getting into these epoxy packages because they're made to be resistant to pretty much anything. It's epoxy resin. In fact, they often use ground up silicon inside of that epoxy to keep it even harder. So I eventually found a video by a friend of mine in France, Antoine, which he called Chips à l'Antoine. You can look it up on YouTube, where he shows a different way of breaking open the packages. It's pretty brutal. You heat it up with your hot air soldering station to about 400, 500 degrees, which makes the epoxy brittle. So at that point, I can take a pair of pliers and crack the epoxy. If you're really careful and do it properly, you can actually crack it open and get the die out of the IC package without any damage to it. Takes a bit of practice, but I had no lack of broken Commodore chips to practice it. So I decided to do that just for fun. My wife was not impressed. First time I did it under the exhaust fan in the kitchen on the stove. She was really not impressed with that one, so yeah. But I actually managed to do it, so that's actually the first two pictures I took of an IC. The one on the left is the first one I ever took of an IC itself. So that's an 8721, which is the PLA chip from the Commodore 128 that generates all the chip select signals, etc. And I was genuinely surprised by just how much detail I could see, even with my cheap soldering microscope. This is about 90 times magnification, at best. So I did some research. You could kind of figure out what is what because you see these big rings going around. Some pins like this 48 here is really connected to that, so I kind of figured one has to be ground and one has to be the 5 volt to feed into it. Mind you, I know nothing about IC design at this point. And I figure that these beefier things will probably be output, or down here you have the beefy things, which is probably outputs, and that might be inputs. So just looking at this picture and knowing that these bond wires, because you see small yellow balls on the picture on the left, those are bond wires. So they're little thin gold wires that are actually vibrated onto these bonding pads and then connected to the outside world. That's how they connect the actual silicon to the rest of the world, through bond wires. So they can't cross each other because they're not insulated. So I figured if I know where the ground and the power is, I can probably number all of the pins on the PLA chip, and right enough, that works. So this is an accurate pin out of the die of the PLA chip. Now you have me really interested. I wanted to know more. So I bought a microscope. So this is an Amscope ME580T. It's a metallurgical microscope, which means it actually shines light through the objective down and reflects it up, rather than a biological, which will have a light source underneath shining through whatever you want to look at. You can't do that with an IC because it's silicon. It doesn't transmit light through it, so you have to use one of these metallurgical ones to do it. So the light source is up here, it goes into a one-way mirror at an angle here, reflects down, you can see the bright spot, and then goes back up again. Then I have a camera mounted on top. I hacked up my own little motorization so I can move the thing around, because once you start getting up to more resolution, you can no longer see the entire IC. You have to take multiple pictures and combine them. Making the motorization is one of those rabbit holes. I'm still working, building mechanical things and robot systems like this now because I find it interesting and fun. Learning about the optics of a microscope was another one of those rabbit holes, and I'm still an absolute idiot, but at least I'm not a complete moron when it comes to optics nowadays. I'm getting better at it. So that has been an absolute learning journey. This control board is absolutely home designed. Fun stuff, yeah. So at this point, I'm getting way better pictures. This is the same chip. Colors look different, but it is the same chip. And if you look really closely, the one on the left is a picture with all the layers left on top of it. So you have the substrate, you have a polysilicon layer, and you have a metal layer. Commodore had a really simple NMOS process where there were only the polysilicon and the metal layers. That's it.
Looks like a platform game map layout.
Yeah, I know, right? So the right picture, I have removed the metal and the polysilicon. This leaves just the substrate layer, which has been doped. And the way you do that, what do you use between the layers as insulation, and you also have a layer on top of all of it called a passivation layer that protects the actual IC from the oxygen in the air around it, is silicon dioxide. It's glass. Glass is not easy to remove. One of the few chemicals that will do it consistently is hydrofluoric acid, also known as the piss of Satan. I cannot buy hydrofluoric acid, thank you, EU. I found somebody on eBay who was selling, they actually use hydrofluoric acid at your dentist sometimes to polish and refine your, if you have dentures or bridges, they actually use it to cut down on the porcelain. So I tried buying it from them. There's 9% hydrofluoric. They just went, no, you're not a dentist, go F yourself. Okay, why are you selling on eBay then, weirdos? Eventually, after a bit of searching, I realized that, well, hobby stores sells glass stainers that happy people use to make happy little flowers on their glasses and little patterns on their mirrors and type of stuff. And I figured, well, if it's something they use for that, it has to be hydrofluoric acid or something similar. And right enough, Armor Etch glass stainer is 3% hydrofluoric acid. So I just slathered that onto the die, and it took off everything. That was not the actual substrate itself, which is the actual silicon plate. Very handy. I was wearing double set of gloves. Has to be nitrile gloves, because if you use latex gloves, hydrofluoric acid likes latex, it goes foof. So don't do that. I was wearing a leather vest, I had breathing protection and a face shield, and etc. And all while I'm doing all of this, just to put a little bit of cream on there, I sit there and thinking about all the happy flower power ladies slabbering that onto their glasses. Yeah. The problem with the hydrofluoric acid is it will go right through your soft tissues and attack your bones. If you were to drop concentrated hydrofluoric acid on your hand, it will literally eat away your bones. You will be left with a Harry Potter arm or hand, right? So pretty nasty stuff. Enough on that. Anyways, what you can see here, some parts of this have a different pattern compared to the rest of it. This was a clue to me, right? You can see it even better on the other part of the PLA structure, which is the ore matrix. If you look at it on when all the layers are present, you can't really see anything. If you go down to the substrate, you have these little slugs here. So this is the way Commodore programmed these PLA chips. They would change the substrate doping mask and nothing else. They would produce the same PLA, metal and polysilicon is the same, but whether they had this structure here or not would turn it into a transistor or not being a transistor. That's the difference. So wherever you have one of these, it's a transistor. In this case, each one of these is an OR gate. So I had to do a lot of research to figure that out. But this was when I was learning this type of stuff. So eventually I had glued together enough pictures to make the whole thing. I put little red dots wherever I had those different structures. I started putting in notes on all of these input and output pins. You probably have them marked on the other side over there. And then I could basically, by looking at this, you take an Excel sheet and you sit down and you make the matrix in Excel and you just go yes, no, yes, yes, no, yes, no. Took a long time, double checking, triple checking, etc. But eventually I actually had the full logic after the PLA chip. I still doesn't really know much about silicon, but I can see the difference between the things, and it made sense to me logically, so I just went on and did it. The problem I ran into is, on the output side of this chip, there were more actual silicon structures between the outputs from this logic array to the pins. So in order to replicate the chip, I had to figure out what those logic blocks were doing. I can't just guess and just ignore them, because that they might be doing something rather interesting. So I had to learn more about silicon. I found this book, very nice book, written in the 70s by, actually it was written by Lynn Conway, but since she was a woman, they had to put a man's name as the first author or they wouldn't be printed. That's really stupid, but it's Lynn's book anyways. Since it is from the 70s, it was the handbook on how to produce and design with NMOS logic, which is, you have three major kinds: PMOS, NMOS, and CMOS. CMOS is everything today because it's way more power efficient. We will go over that as well. I showed this at the first time I gave this talk at VCF East, and one of the Commodore chip engineers just shouted from the audience, "Yeah, we all had that book on our desk." So this is the book the Commodore people learn how to do their chip designs from, which is pretty cool. So it's also where I learned how a transistor actually works, or a MOSFET, which was always black magic to me. Not gonna go into the details of it, but anyways. Commodore had three processes: NMOS, HMOS, and HMOS2. It's the exact same process. They didn't change anything. They just shrunk it to make it smaller. And you can actually see which process a Commodore chip was manufactured in. If its number starts with a 6, so 6502, it's NMOS. If it starts with a 7, like the 7501 in the +4, it's an HMOS. And if it starts with an 8, it's HMOS2. So, happy little side note. Anyways. So, if you look at how NMOS works, we take a normal NOT gate that will take a 0 and output a 1, and a 1 and output a 0. That's the normal schematic diagram. This is how you can actually implement it using a FET and a resistor. So you have a pull-up resistor, and the FET can pull to ground. So if you have a 1 coming in, it will connect it to ground, and the output will be a 0. If you don't have a 0 on the input here, the transistor is open, so 5 volts will flow to the output. 0 in, 1 out, 1 in, 0 out. That's an inverter. And since they can't put a full resistor inside of an IC, they instead using something, technical term, a depletion mode device, which is a specially designed MOSFET, NMOS transistor, that's designed to work like a very crappy resistor. It's basically a depletion mode MOSFET that has the gates tied to the source. This is, by the way, the reason why NMOS draws so much power and gets so warm, because of those pull-up resistors. You get a power loss in it whenever you pull it to ground, because now it will flow current. So if you look at a circuit diagram over there, this is what it actually looks like inside of an IC. This is from the Commodore 128 NMU chip. I love that picture because you can actually, it's a textbook example of how to design an inverter in NMOS logic. And this is kind of the representation of it. I'm probably not going to go into all of the details, but it's pretty cool how you can get this deep in and actually learn how to see these type of things. I no longer see this as just a bunch of lines. After the months I've spent on this, I actually see this and just go, yeah, that's an inverter. It's kind of funny how that happens.
Do you see the three-dimensional shape of it, or do you just see the cartoon two-dimensional shape?
That's the trick, right? So if I go back to this is how a side cut of NMOS. You have the substrate, which is the actual silicon die that comes straight from the boule, so the silicon wafer. You have the source and drains, which are doped. Either the whole substrate is either p-doped or n-doped. So p-doped is boron and n-doped is arsenic, I believe, to introduce either a surplus of electrons or a lack of electrons in the various areas of the silicon itself. And then you have insulation layers going in, that's glass. And the gate itself is polysilicon, so that's basically silicon material that has been sputtered onto it. So they basically vaporize it using plasma, and then it lets it fall onto the IC in those specific areas, where it formalizes and turns into a polysilicon layer, which can conduct electricity. It's also doped, of course. Then you have vias, which are traditionally done in tungsten, I believe. No, not tungsten. Palladium, or it's pretty rare the things they use for these vias, which is like a via on a PCB. It's a connection through to various layers.
And and they do it in layers, or?
Yeah, correct. And you have the metal layer on top, which is, in Commodore's case, aluminium. Once again, they vaporize the aluminium and just let the droplets fall. The way they do that is they put extra glass layers on top with holes where they want things to stick.
Oh, yeah, okay. That's all the glass layers.
There's a lot of layers involved inside of the IC. This picture is a lie, because everything looks neat and tidy in separate layers, right? So you have the doping, you have the insulation, you have the gate, you have the metal layers, and the vias in between. What actually happens is, of course, when they put the insulation on, there is nothing between this and the metal, so the metal is actually going to end up fairly close down here, whereas the insulation in the gate builds height, so you will actually have varying heights of these structures. And you can actually see some of that on the picture here. The little stick going over here on the bottom, on the horizontal stick, that's polysilicon. The connection underneath, the wide one that goes vertical, that's a doped area in the substrate. And you have the same up here, so you have the doped area in the substrate. That's the doped area behind there, with polysilicon on top. And these just basically add on to layers. You have the same over here. The metal here, the white one, that's metal layers. You can see how it comes from here, and then there's a line. That's because it actually goes up a bit to go over the polysilicon, and then drop down a little bit again. So it actually shaped like a bridge over that polysilicon. So from a side view, it's really irregular.
It'd be
So
cool to see that picture.
what you actually get with a microscope, a good proper microscope, is once you go up in resolution to take pictures like this, your focal depth is easily measured in microns. So if I focus on the metal layer here, the polysilicon layer is going to be fuzzy, it's out of focus. And now we're talking maybe a micron of difference between the two. I can literally just twist my focus, the Z axis on my microscope, and focus on the metal, the polysilicon, the substrate. Is really that thin of a focal depth on it. And because of the varying heights of these structures in there, it becomes really tricky to get good photos. So what I've ended up doing since I took these, you can see it's all fuzzy, is I now use focal stacking. So I take tons of pictures with various Z axes, and then I use software to do focus stacking to combine the sharp parts of each picture. Which makes much prettier pictures. I suck at it, but there are some absolutely fantastic IC shots out there.
Could you do micron Gaussian splatting or photogrammetry?
Probably. There's tons of people out there who are vastly better than me at this stuff. I've gotten in touch with quite a few of them. I'm talking to them. So Antoine, for example, who I mentioned earlier, who taught me how to take the ICs out. His day job is using microscopes to check and control pollen. That's what he does for a living. And then he takes his microscopes that he has and uses them to look at ICs during his downtime for fun. So that's the output section. As you can see, I've already gotten better at taking pictures. On the left-hand side, you can really see that focus problem, right? That's focused on the polysilicon, so the reddish ones, or pink ones, are really focused, and the white metal layers are just fuzzy mess. So that's one block. One trick that most designers did a lot back then, they had only rudimentary design software. There was no HDLs to describe the hardware in a synthesis software. This is all hand laid out. It's black magic. They used all the tricks to save space and transistors, etc. But what they would often do is they would design something, make it slightly generic, and then they would just copy paste it. A lot. So all the output blocks are exactly the same. The advantage for me is, of course, if I reverse engineer one of them, I've reverse engineered all of them. So I took that shot. I took the shot where I had removed everything with the hydrofluoric. So what you see here is the doped areas of the substrate with some remnants of the vias still sticking around. I combined those and made this drawing in Inkscape, which sadly is still one of the best softwares for doing so. Red for polysilicon, blue for metal, green for the doped areas, and the circles for the vias. And then I just took a piece of pen and paper and kind of unfolded this compacted thing to turn it into this schematic, which you can then, with a bit of work, condense even more into actual logic gates. And this is literally just a D-latch on the output. So once I knew that it was a D-latch and which signals into the silicon was what, I could figure out which of these D-latches were actually used or not, and realized that two signals were using the D-latch on the output to do some typing, which allowed me to then finally write Verilog code to represent the entire PLA. So that's pretty much the result of all of this work, to replicate one of these chips, the PLA chip. Very regular structured chip, fairly easy to work on. And then I made a small replacement using a CPLD, and some debugging later, I had a functioning replica of that chip. Yeah, that was a lot of work. There were some issues still, and trying to figure out what was what. I ended up having to buy an old HP logic analyzer from the 1990s because it was one of the few things that still had enough channels available for old computers like this. So a modern logic analyzer, there's very few of them that has more than 16 channels because everything today is a serial bus. 16 channels will cover the address bus in this computer, and then I still need the other 16-bit address bus and the data bus and all the control lines, and there you go. So that old HP has 168 channels, and I can add another 300 or so when I find the boards. But yeah, that chip works. The logic equations for it is up on my Git. And Evie from Backbit actually sold a C128 PLA replacement for a while using the equations from my reversing work. So that's pretty cool. Of course, at this point I was kind of stuck into things, so I bought a microscope. And now we're starting to get a bit wild. So that is a Olympus BH2 from 1985 mounted on a Nikon MeasureScope 25 kilograms cast iron base with a completely home-built motion stack. You have Y-axis, X-axis, Z-axis, tip and tilt, all motorized. So I'm currently still working on software for this one. I've replaced the camera. It's now a USB camera because that allows me to do live pictures much better. The reason for the live pictures is I use autofocus algorithms to automatically level the die. So I pick 3 of the corners, and then I move one up and down with the Z-axis until it's in focus, then I tip and tilt the die to make sure the other 2 corners are in focus, and then I repeat that process a couple of times so I know that the die is completely level compared to the objective. It's the best way of getting really focused pictures. It was no fun to do that manually.
But in the old days, they would actually have people processing the negatives and...
Well, the chip designers at Commodore could just look at their masks, of course. They designed the damn thing.
Yeah, but if they were going to have a discussion, then...
Oh yeah, they had better microscopes. They were probably using microscopes like this, and in fact, Bill Hurd has a fantastic story where we ran into a couple of chip guys sitting in a lab, turning the light on and off. So they were looking at a chip under a microscope and had masked off sections of it, and they would turn the light on and off because that was enough photons to excite one part of the chip to enable a gate. So they were flipping the light on and off to see how the chip was reacting. You also have, I mean, this is amateur gear, still. You have what's called a micro probing station, for example, where you not only have a microscope, you also have tiny little mechanical electrical probes where the tips are measured in microns, and you have small actuators that can actually place them onto the IC die, so you can connect all of those bonding pads using these microprobes, and you can in fact also even connect inside the chip itself to do tests and runs, etc., and modify things, whatever. So there are people I know that play with that in their basement too. For fun. Yeah. As I said, there's a lot of rabbit holes involved in this. But that's my current microscope that I use. I've evolved the motorization options a lot since then, etc. Yeah. This is pretty recent, so what I'm working on right now is I'm re-implementing the MMU chip from the Commodore 128. My ultimate goal is to be able to build one of these without using a single actual Commodore chip, but still the original PCB, because I'm crazy like that. It's fun. And the 3 chips that are absolutely uniquely Commodore 128 is the PLA, the MMU, and the VDC chip, which is the 80-color video chip. So I've done the PLA. I have a half-working MMU already. For that one, I haven't actually done any reverse engineering. I just re-implemented it from specifications because it is still a fairly simple chip and there is no weird timing constraints, etc. I will then reverse engineer the 80-column video chip or do a re-implementation of it. I don't know which will be the easiest yet. I have a full set of pictures of it, but yeah. And as I said, my plan is to basically build a C128 with no original Commodore parts. Just all brand new things that you can find. So, that's it for me. Any questions? Yeah?
So, the biggest question I have, which doesn't with respect to all the details you've given, why is the Commodore 128 such an interesting computer?
For me personally, or just in general?
You know, like I upgraded from C64.
Yeah.
And my dad took me to the computer store.
Mm-hmm.
And I was going to buy a Commodore 128 because it was the next one.
Yeah.
And they said, by the way, we have this Amiga.
Yeah.
And so I never saw the 128.
No, exactly.
I got the Amiga 500.
Yeah. And that was kind of there was two things that doomed the 128 really, or the 8-bit. The 8-bit series was dying at this point anyways. It came out at about the same time as the Amiga, so it was overshadowed. And there were not enough of them ever sold, even though they sold million. There were never enough of them sold to interest the software developers, because they all knew that there were tens of millions of C64s out there. This computer can also be a C64. Why would I make something that would only sell to a tenth of the customer base, right?
Yeah, what new could you do? Like,
yeah.
What was the new stuff?
For games, there's almost no 128 games. I think there was only 2 or 3 games developed back then. Now you have X3 robots. And there are a few games coming out that's actually using the 128 today, but back then there was almost no games. There were, however, quite a bit of productivity software that used the 128. So there's quite a few BBS softwares that's 128 specific. It has the 80-column screen, which is great for a BBS. You have more memory, which is great for a BBS. You have way faster floppy drive, because the 1571 and the 128 together makes it burst mode capable, which is an easy 5-6 times the standard speed of the C64 floppy without doing any form of software modification. So in that way, it's absolutely great. That was actually the burst mode on the 128 with the 1571 was the original design speed for the C64 and the 1541. It's true. That was the intent.
So the upgrades were graphics bandwidth and memory.
Yeah.
But like if you went to Atari took market because they had MIDI.
Yeah.
And
kind of. We'll get to that point. I will explain the history behind the Commodore 128. So the 128 was Commodore engineers, and Commodore was always a bit weird in the fact that it was extremely engineering driven. There were no focus groups, there was no marketing and sales team who would have input on product design. Engineers would design products, and then they would see if anybody of the Commodore subsidiaries, country specific, etc., would actually buy them to sell them. That's how it worked at Commodore. So pretty much every single Commodore computer that was designed was a grassroots project by the engineers. They were building the computers they wanted to build, and if the rest of the company wanted to sell them, great. Sure, they had input, etc., but much of their design process was truly engineering driven. So this started basically as an idea that Bill Hurd had at one point, because he had just come off the TED project, which is the Commodore Plus 4, the Commodore 16, etc. So he was trying to do a new project, and the TED is not C64 compatible and was getting a lot of shit because it wasn't. It was never intended to be. It was intended to be a dirt cheap computer. The Commodore 16 was originally designed to be sold for $49. And if it had come out in 1984, costing $49, they would have sold a shit ton of those machines. That was the whole purpose of it, but Commodore marketing fucked that part up. So, yeah, the Plus 4 is an abomination. So at that point, Bill and Dave, because Dave Haney is seriously involved in the 128, decided that this time we want to do something that's actually compatible. And we have a runaway success with the Commodore 64. How about we build a better Commodore 64? So they set out to do that. And due to the way the Commodore 64 is designed, you pretty much have to start with a Commodore 64 as its core design, because the entire Commodore 64 is driven by the VIC chip. The timings of the VIC chip, the bus demands of the VIC chip controls the entire Commodore 64 design. There's no way around it. If you want to be compatible, it has to be, hardware-wise, a VIC-2 in that type of machine. So what can you do? Well, you can add more memory. Of course you can, right? That's always a good idea. We could probably make the CPU faster. Let's say, bump it up to 2 megahertz. We have 2 megahertz 6502s, why not, right? Will it be incredibly useful? No, we can't run it at 2 megahertz when the VIC-2 is using the bus, but we can use it in the borders, for example. So on the top and bottom borders, we can enable the 2 megahertz mode because the VIC is not using the bus, and off you go. Now we have a slightly faster computer. If you blank the screen, hey, guess what? Now you have full 2 megahertz available, right? What else can we do? We can add an 80-color video chip. We can't remove the VIC. We can't redesign the VIC because we don't have time to do that. So we can put in a more beefier video chip for a monitor, like, well, Bill Hurd actually wanted a color 6845. He asked the chip designer of the VDC whether it was basic a color 6845, and the guy goes, yeah, pretty much. Except it's nothing like it, of course. And if you have 80-column text, now it becomes a lot more useful for productivity. You can use it as a terminal for interacting with computers at work, etc. Right? It opens a lot of options, and these are still fairly easy things to tack onto a 128. Then, as they were working on designing all of this, because you need a new PLA, you need a new MMU to do the address translation, to do the memory banking, etc. You need new software, etc., which takes a lot more space. The 128 BASIC is huge compared to the C64 BASIC. They were working on this, and they had promised 100% C64 compatibility. So the QA team and the sales team had taken it upon themselves to break the 128. They were always hunting for software or hardware that didn't work on the 128. They just absolutely enjoyed finding issues like that. So they would show up, haha, this doesn't work. And the engineers would just go, oh yeah, click, now it does. Typical Commodore fashion. So the two big ticket items that ended up was the Super Saxon cartridge, which we all know is horrible. Because the Super Saxon plays with some of the lines in the cartridge board. You have two control lines in the cartridge board, game and XROM, that are used to tell the C64 that, hey, I'm a game cartridge and I have an expansion ROM, and etc. You're supposed to connect them to either ground or 5 volt. That's it. Super Saxon has them connected to a logic chip and play silly games with those control lines. And that has been a problem even on C64s, because if the timing of the C64 is not absolutely spot on, Super Saxon does not work. On the Commodore 128, because of the completely different EEPROMs and system software, takes a lot longer to start. At that point, Super Saxon just missed the boat completely, and the game would just ignore the cartridge. Problem. How can we fix that problem? Right? We can't scrap the system software, we have to figure out something. The other big problem that child they came up with was the C64 CPM cartridge, which is a full Z80 computer inside of a cartridge for the C64. It pulls the DMA line in the cartridge port to disable the built-in 6502 and just takes over the rest of the computer. The cartridge worked in the 128. The only problem is it is a full computer with a ton of stuff inside. It uses a shit ton of power. So when you plugged it in, it would rapidly exceed the power budget allocated to the power supply. And they already had a 2.5 amp switch mode power supply, pretty expensive already at that point. If you had to crank that up to 4.5 amps, it would explode his budget. The budget would be gone for everything. So that was also a big problem. The cartridge worked, but he couldn't afford it from the power supply budget. And you can't force people to go and buy a new power supply to run their cartridge. They actually did with the CPM cartridge. when you bought the CPM cartridge, it came with a more powerful power brick for the C64, just to make it run at all. So Bill Hurd was in the local pub one evening thinking about that problem, and probably had a bit of a beer-driven if Muhammad can't come to the mountain can come to Muhammad moment. Got the brilliant idea that, well, if I take the Z80 out of the CPM cartridge and put it inside the system, I can run CPM, I don't need the CPM cartridge. And if I make it boot with the Z80, I can probably have that checked for that Stilly Super Saxon cartridge as well. So that's what he did. He ambled back to the office, grabbed one of his door stops, e.g. a ZX81, ripped it apart with his hands, picked the Z80 out, and when the rest of the engineers came back the morning after, they go, hey, by the way, it's got a Z80 now. So that's how it ended up having a Z80. Now you have that truly weird system. That's when they started doing the free systems in one marketing and all of that type of stuff. They also promised, even on the box of it, expandable to 512K, which it isn't. It is, in fact, technically capable of 256K. The system software is designed for a 256K system. The NMU chip is designed for a 256K system. Due to reasons, and I need to remember to ask Bill about that sometime, is instead of using 2 extra address lines as the output, which would allow 4 banks because you have 2 pins, you have an upper bank and lower bank coming out of the NMU chip. If that had been extra address lines, I have a hunch of why that happened. Due to the very compressed timeline of the Commodore 128. In fact, from the first idea email to showing the computer at CES was 5 months. So they literally designed this system plus the custom chips that goes into it in 5 months. And due to how long certification takes, for a lot of that time the PCB was already with FCC to do all of the certification testing. When you do the certification testing, you are limited in what changes you can make to the board. You can add and remove passive components. You cannot add and remove ICs.
You was engineer pictures of where's the original documentation? Is it disappeared?
Yes, most likely.
Okay. So it's the documentation.
The Commodore's collapse was absolute mayhem. There were people, Commodore engineers, Commodore employees walking out the door with whatever they could grab. There were people robbing computers of their RAM chips.
If you watch the Dumper video,
yeah, it gives an idea of it.
One of the engineers actually sitting inside his Amiga 3000 and ripping out RAM chips because I need them at home.
Yeah, exactly. It was pretty much the same with documentation. Some people walked out with it, some people went through it in the skip. It was just absolute mayhem. There was no organized handover or whatever, right? It was just complete chaos. So the original documentation is gone. There are, supposedly, I think they probably still exist. If they do, they're with Dave Haney. Because the way the dynamic works, so Bill Hurd was the lead system engineer for the Commodore 128 project. Dave Haney was his second in command, to a large degree, on the system. And they have worked together pretty well because Bill Hurd is the wild ideas man. And because he has no actual education, his job before Commodore was a TV repair guy. That's what he did before he joined Commodore, pretty much. Dave Haney is university educated in electrical engineering. So he does all the number crunching. So if you look at the C64, the timing restrictions on the C64 is all over the place because it was literally just a prototype they threw together to show that, hey, this can be a computer. The Commodore 128 is designed with timing constraints in mind. So Bill Hurd would have a crazy idea. He would just start, can I do that, Dave? And Dave would look in his notebook and go, yeah, you got 5 nanoseconds left. Right? So in the 128, the timing is tighter but controlled and working. So in some cases, the C64, you actually have a minimum timing constraint. If something is generating a signal too fast, the computer stops working. Whereas in the 128, when I made the PLA chip, the original PLA chip has 35 nanoseconds of delay from input to output changes. The replacement chip is 6 nanoseconds. And the computer works just perfectly fine. No problem. Because it's designed with those kind of timings. But yeah, absolutely. Commodore's collapse was just absolutely amazing. There are things starting to show up lately. There are some people, former Commodore engineers, who have kind of become the designated archival people for some of the other ones. So if they don't have room or whatever, they give them to those people instead. So also, you might have seen them on the internet. You have the International Commodore Historical Society, which started a couple of years ago, 5-10 years ago, which have gained a lot of respect and confidence from old Commodore people, not just engineers, but from all over Commodore. So they have actually started also gaining a lot of internal documentation, both from engineering, from sales, from marketing, from legal, from finance, all over the place. So, for example, just last year, he got enough data to finally calculate exactly how many Commodore 64s have been sold from annual reports within Commodore, internal annual reports. We know the exact number of Commodore 64s and 128s, down to the 100,000, it's 14.7 million, I think, in total. Not 21. But we can't actually tell how many C64s and how many 128s, because for 2 years they didn't separate them. They just called them 8-bit computers in their annual report. So we can never tell. We can make educated guesses of how many the split is between them, going from other sales figures, but we will never know exactly what it is. But now we actually know how many computers we sold. So that's starting to have an effect as well, that these documents are starting to show up. But I do believe that much of the actual hardware engineering source files and design files, etc., they're probably lost forever. I would not be surprised if a lot of them went bang when the CBM max was turned on. I do have a happy artifact at home. I actually have an MOS wafer from the IC factory with the 80-column video chip on it. And right enough, it's been binned. So binning is when you have a full wafer. They actually use those micro probing stations to fire up the chips and run automated testing on each chip before they cut them out and package them. Because there's no point in packaging a broken chip to just test it afterwards. That's just a waste of money. And when they fail the binning, they usually put a little mark on them with a black marker or something to just mark that this is a bad time. And the story has always gone that the 80-column video chip has an absolutely horrible yield on how many chips work per wafer. And right enough, there's a 25% yield on the wafer I have. So 75% of the chips are just broken from manufacturing. So those are bad in some way. In many ways. I could talk about trivia on the 128 for hours and hours. Yeah. Yes?
Have you seen the video from Jeff Geerling about reverse engineering Raspberry Pi?
No.
It was around last week or something.
No, I've
where it's X-rayed or something, and where you can go layer for layer.
For modern chips, it becomes a heck of a lot more complicated. First off, modern chips are so dense, and the actual node size, so the size of the individual components in it is so tiny that you can no longer use optical microscopes. You can't look at them in detail.
You got the whole from the PCB and the chip and everything.
Yeah, so you need to use scanning electron microscopes to actually get any form of detail out of it, which means you can't get a picture of all of it, because you would spend 1 year just scanning to make a composite image of the whole thing. On top of that, the Commodore chips has one metal layer, right? Modern ICs, you count those metal layers in tens, as in 40, 50, 60, 100 metal layers. It's gonna get even worse now, because On most of the chips manufactured today, everything, you have the substrate and everything is put on top. Intel is currently working on a process where they take the power and inject it from the other side, from the bottom of the substrate. So you have power delivery from one side and the logic on the other side. That will make it even harder. On top of that, many modern chips, Raspberry Pi included, have protection features built in. They will have metal layers with grid patterns for EMI reduction to reduce interference in and out, but also to obfuscate what's actually going on inside the chip.
Yeah, but you could browse all the layers
Yes.
in an application though. So
Oh, yeah,
it's
no,
open source.
He's got it, of course, because, yeah. So, the design files, of course, they're available at some point to somebody, even for more modern chips, absolutely. But it's getting really hard to do reverse engineering on modern stuff, especially